Hello, class 12th physics chapter atom. So important questions. First, define ionization energy. The minimum energy required to remove an electron from its ground state in an atom is called ionization energy. What is its value for hydrogen atom? So its value directly, if we will write, then its value ionization energy is equal to 13.6 electron volt. Direct answer. But how has it came? It is because we know that energy required to excite an electron from lower level to higher level is given by E2 minus E1. It is the same as it releases the energy, higher energy, lower energy. So if E2 is the state corresponds to infinite energy level, so value of E2 will be 0. Why? Because we know that En is equal to minus 13.6 upon n square electron volt. So if n is infinite, so that value of E will be 0, and E1 corresponds to ground state because they have asked for hydrogen, so it's ground state. If we want to ionize it, then we have to remove first electron. That is the only electron in it. So for that, n equal to 1. So E1 is equal to minus 13.6 upon I misplaced point upon 1 square. So that is minus 13.6 electron volt. So putting it here, so it will be 0 minus 13.6. So that is why 13.6 electron volt. But it is actually 1 mark question, so we can directly write the answer. Otherwise, it's up to you whether it is of 1 mark or 2 mark. You can give that solution here. Write the expression for Bohr radius in hydrogen atom. Well, we will have a quick derivation for it once again. So remember, centripetal force is equal to electrostatic force, and from here, if we cancel it, so mv square r is equal to ke square, and we know by Bohr hypothesis that mvr is equal to nh upon 2 pi. This is the way you can quickly derive the relation. From here you will find v is equal to 2 pi ke square upon nh, and putting it back here, they are so messed up I have done. So mv 2 pi ke square upon nh and into r, mvr equal to nh upon 2 pi. So r will be equal to n square h square upon 4 pi square ke square m. So this is the relation, we can write it there. And Bohr radius means for ground state radius, so put n equal to 1, so that will be the Bohr radius. So Bohr radius, answer is RB. We can write like this. Actually it is R1 for first energy level, so it is h square upon 4 pi square ke square m. Sometime if it comes in MCQs, then what will you do? Maybe they have put this value of k also, so putting that value, h square upon 4 pi square k is 1 by 4 pi epsilon naught e square m. So finally it is 4 pi will get cancelled, only single pi will be there, and this epsilon is in the denominator of denominator, so it will come up epsilon naught h square upon, now only pi is there, and e square is there, and m is there. So this is the Bohr radius. So how you can do it? See, I have hardly taken 1 minute to derive that and to put the value, respective value here, and it is an it might be come as an MCQ, so you have to just take that answer, you have to just mark that answer. Okay, so that's not a big issue. Right, next, what is the ratio of radii of orbit correspond to first excited state and ground state of hydrogen atom? First excited state means if these are the energy levels, so excited state means this is first energy, second energy, third, fourth. So if it was here, so this is its first excited state, that is second energy level. Second excited state, that is third excited state, that is fourth. So when the word comes excited state, it means first excited state, it means they are talking about n equal to 2, and here we know ground state is n equal to 1. So what we will do, because they have asked for ratio of radii of orbit correspond to first excited state, so this upon this, so what we will do, r, I want to just make it sure that I'm putting correct values, so I'm putting r subscript excited state, and upon r ground state, gn ground is equal to, we know that r is directly proportional to n square, so that is n excited state square upon n ground state square. So excited state, first excited state means 2 square upon ground state means 1 square, that is 4:1. Next, the radius of innermost electron orbit of hydrogen of a hydrogen atom is this. What is the radius of orbit in the second excited state? Second excited state, actually they are talking about n equal to 3. All right, so we know that now we can put these symbols r1, because innermost will be the first, or directly first we can write anything which is in the initial condition. So r1 upon r3 I am writing. I hope you will understand that thing. Otherwise you can write second excited, for second excited state n equal to 3, you can mark that first. Okay, so r1 upon r3 is equal to n1 square upon n2 square. n1 is 1, and 2 is actually, instead of n2 I am writing n3. There are some mix up there. n3, that is third state. So because they have asked for second excited state, that is why it is third state. So it is 1/9, but it is not over yet. So for r3, if we set, because we have to find the radius of second excited state, that is r3, you can use any subscript, so no need to worry about that I have put 3. If you would put 2 or r dash or anything else, then your marks might be deducted. No, not like that. The processing should be correct, and that's all. So r3, it has gone here, so it will be 9 times r1, so that is 9 times 5.3 into 10 to the power minus 11 meter. I think you can do the calculation, or if I have to do, then 9 5s are 45, but 46, so it will be 46. It's my approximate calculation. So if you are new to my videos, these might be make you a bit anxious that how I'm doing this. So these are approximate calculation, and now I will take the advantage of that order of magnitude and that scientific symbols. 4.6, I have decreased the value here, I will add 1 here, so it will be 10 to the power, oh my god, 10 to the power minus 10 meter. So more scientific way to represent. Okay, next, find the ratio of energies of photons produced due to transition of electron from second permitted energy level to first level. So we have to calculate energies of photon. Actually, simply the energy difference between these energy levels and highest permitted energy level to first permitted level. So there are two parts. First part, so E equal to second permitted minus first permitted. And in such questions, they give the value of En most of the times. So sometimes students think that they have to memorize this. Yeah, memorize this, but in case in such type of questions, most of the time they give the value of En. So but still, don't relax yourself that okay, this will be given in the exam. No, consider it that as if it would not be given in the exam. So E2 minus E1, E2 minus 13.6 upon 2 square, and minus and again minus 13.6 upon 1 square. So this will be 13.6 by 4 minus and plus 13.6, that's all. And if you divide this, it will be, this time no approximation, this time actual, 4 3s are and 4 4s are, and plus 13.6, which comes out to be 10.2, and with positive sign, yeah, 10.2 electron volt. Okay, and now highest permitted energy level. So highest permitted energy level is infinite. So here B part, E infinite minus E1. So I'm not doing it anymore because I have done similar kind of question in the beginning here. Oh, or I will do that because I didn't give the solution there. So okay, consider it for both of these questions. So here it is 0 and minus 13.6 upon 1 square. So that is, it will become plus 13.6 electron volt. Next. Alright, next question. The ground state energy of hydrogen atom is 13.6 electron volt. What are kinetic and potential energy? Just remember this picture in your mind, like if kinetic energy is x, then potential energy, in fact total energy is minus x, and potential energy is minus twice of x. So keeping this picture in mind, we can say like in reply, like the answer is kinetic energy is equal to negative of total energy, that is minus of minus 13.6, and that is 13.6 electron volt. And the potential energy is equal to twice of total energy, that is twice of minus 13.6, and that is 13 to the 26, 27 minus 27.2 electron volt. So to explain why is it so, we can say like we know that I will begin with that centripetal force is equal to electrostatic force for orbiting electron. For more detailed analysis of this, you can watch my video about this Bohr's hypothesis. So it is mv square r equal to ke square, then divide it with Bohr's postulate expression, and from sorry, I didn't meant that we can do it here only. So r get cancelled, so mv square equal to ke square upon r. This is so kinetic energy is equal to half mv square, and mv square is this, so it is half ke square by r. This is the first thing. Second, we know the potential energy of two charges is k q1 q2 upon r. So here k is 1 by 4 pi epsilon naught. K q1 is electron, q2 is proton, because in hydrogen atom only these two things are there. Proton denoted by E because its charge is plus E and electron charge is minus E. So, and upon distance between them is R, so it is minus ke square by R. And if we add both of them, we will find energy, which will be half minus 1 is minus half ke square by R. So this is how we can say that kinetic energy is equal to total energy, but with negative sign. This is what we have done here. And potential energy is twice that of total energy. So this is what we have done here. For more detail, you can watch the video on this topic. Link is in the description, and if not, then you can go to my previous videos. Why classical model means Rutherford model for an atom of electron orbiting around the nucleus, not able to explain atomic structure. Now see, there is actually, they are asking about the limitation of Rutherford's model. So here they are not asking about electron arrangement and all that. What they are asking actually is that limitation in which Rutherford couldn't explain why electron will not radiate, why electron will not fall into the nucleus. So we will write the answer according to classical theory. Orbiting electron is in the influence of centripetal force, and hence centripetal acceleration. Okay, an accelerated charge radiates EMW, electromagnetic wave, and if electron radiate energy so finally it will fall in the nucleus. So finally it will lose all the energy and fall in the nucleus. In this way, atom is not stable. So Rutherford model couldn't explain the stability of atom. Next, what is the maximum number of spectral line emitted by a hydrogen atom when it is in third excited state? So there is not a formula for that. It is just the mathematics, just the our understanding will do the trick here. First energy level, second energy level, so it is third excited state. Oh, I don't have enough space here. This is third, this is fourth. Actually this fourth is third excited state, third excited state. So how many maximum number of spectral lines? So first spectral line will be this one, second one will be this, and third one will be this. On the other hand, if it has jumped here, so it can come directly like this, or it can come in two steps. There is no other way to return to the ground state. So these are all the possible transitions. So 6, direct answer is 6, nothing else. It is not looking like 6. Okay, in hydrogen atom, an electron undergoes transition from second excited state, means n equal to 3, to first excited state, means n equal to 2, and then to ground state. Okay, so we can draw this. Second excited state, 1 2 3, that's enough. 1 2 3, second excited state to first excited state, and then first excited state to ground state. Identify the spectral series to which these transitions belong. Find out the ratio of wavelength emitted radiations in two cases. Okay, so many things they have mixed in a question. So identify spectral series. So first transition, second excited state to first excited state, this belongs to, because it has returned to second energy level, so this belongs to Bohr. And other one, second first excited state to ground state means first to first energy level, this will be Lyman. They can also ask which one of them can be seen through naked eyes or visible, so that will be the first transition. Okay, now they are asking that find the ratio of wavelength of energy emitted. So ultimately what we will do, we will find the energy in first transition. Okay, so first transition, second excited to first excited, means E3 to 2 upon, then first excited to ground, means 2 to 1, that is equal to E3 to E1, means E3 minus E2 upon E2 minus E1, and that is E3 So E3 is minus 13.6 upon 3 square minus, and again minus, so I'm putting plus. So be careful about it. One minus and other minus, because this energy is in negative, that is why plus. So 13.6 upon 2 square upon minus 13.6 upon 2 square minus, and again minus, so plus 13.6 upon 1 square. So this is equal to 13.6 upon 9. So this will be minus 9 ones are 9 and 9, approximately 5s are 45, and plus here 4 3s are 4 4s are, and upon minus 3.4 and plus 13.6, and this will turn out to be 1.9 upon, is it 1.9? Yeah, of course, 1.9 upon 10.2. So that's all. Now actually they have asked for the wavelengths, so we know actually very less space is there. I expected that I could do it in this much space, but I couldn't. So maybe I will use another sheet, or what else we can do. We can use this space. Okay, so actually find out the ratio emitted in two cases. Now there is a trouble whether we have to put this wavelength in numerator and that wavelength in denominator. Yeah, order is that. So actually we have to find, this is done. Now we have to find lambda 3 to 2 by lambda 2 to 1. Next calculation will be there. So what about this question? I don't know. Anyway, sometime it happens. Okay, so slight adjustment. Okay, that's enough. So we know that E equal to hc by lambda. So lambda will be equal to hc by E. It means lambda 3 to 2 upon lambda 2 to 1 is equal to hc by E 3 to 2 upon hc by E 2 to 1. See, this kind of these questions might confuse you in the exams, but if you just understand the logic behind how they want to frame this question, then you need to stick to your basics. See, the way in which I am solving it, it's we don't have to do something extraordinary, just going through the simple mathematics. So now this will get cancelled and this will be reciprocated, because this is in the denominator, this is in the denominator, and in such a way this will multiply here, this will multiply here, hc will get cancelled. So ultimately this will go up. And we know 2 to 1, we have just reverse of this. So here we had this 1.9 upon 10.2, so we will write its opposite here, 10.2 upon 1.9. so if you know 19 table of 19 5s are 95, 7 left, 4 5.4 I guess. approximately 5.4. Which kind of ratio is this? But what sometime we can write it in this way, or if you want to end it here, yeah, 102 by 19, this is also ratio. This is not the ratio, actually I have calculated it into decimal places. Otherwise you can leave the answer here by removing these decimals. That's all. Now, using Bohr's postulate of atomic model, derive expression for radius of nth electronic orbit, hence obtain expression for Bohr radius. See, the question which was in the beginning has came here in the form of derivation, and we did it. So now how to do that? Now space is very less, so I will be skipping most of the terms, because this entire derivation has been done in the main video. So here I am just skipping many terms. So first of all, you have to draw hydrogen atom here, plus E here, minus E, with velocity v, n, radius r, n, mass m. So centripetal force is equal to electrostatic force, that is mv square by r equal to k e square by r square subscript n subscript n subscript n. So then it will be mv square rn. Actually I have cancelled and cross multiplied, ke square. Now we have done it many times, so don't bother about it. Then put it in equation 1. Now we know that by Bohr's postulate, so mvr equal to nh upon 2 pi. So we will divide both of them, and I am directly writing what was the outcome of that. Equation 1 divided by equation 2, 1 divided by 2, many students say that it is 0.5. Okay, so it will be v equal to 2 pi ke square by nh. Now we will put this value into equation 2. 3 into 2, so it will be m 2 pi ke square upon nh rn equal to nh upon 2 pi. So rn equal to n square h square upon 4 pi square, okay, ke square m. And for ground state, n equal to 1, so r1 equal to h square upon 4 pi square ke square m, which is called Bohr radius. That's all. So we did it earlier also, and you can put even value of k also, and further you can solve it, make it more simpler, actually more complicated. Show that radius of orbit in hydrogen atom varies as n square. Oh, surprisingly I picked both of these questions. Actually what we did in earlier question here, that's all. This is what we have to do there, and that is why I am not doing it, and that's all, because Rn is directly proportional to n square. So exactly this thing should be copy pasted there. I am not doing it again because we have done it in the lecture video as well as in this question and earlier question also. So I'm skipping this. Don't cut my marks for that. All right, and don't do it in the exam if to such type of question comes that I have done it earlier in question number so and so, so I'm not repeating it. Well, okay. When an electron in hydrogen atom jumps from third excited state, third excited state means n equal to 4, to the ground state n equal to 1, how would de Broglie wavelength associated with electron change justify just beyond the concept? The question is just beyond the concept. Actually, this time any student can think about this jump 4 to 1 and emitted radiation, and can think that E equal to hc by lambda, and they are talking about this lambda. No, they are not talking about this lambda, they are talking about de Broglie wavelength, and that de Broglie wavelength is directly related to h by p, momentum of that electron. So lambda, they are talking about this lambda. So those students who didn't gone through the not yet gone through the dual nature of radiation matter chapter, they could skip this question right now, and when they will go through that chapter, afterward they can solve this problem. But for others, I am solving this. So here the thing is, it is basically they are talking about its momentum, and we know its momentum is h by mv, and we know this v is directly inversely proportional to n. So ultimately we can think, we can do it here. De Broglie wavelength, actually it is Broglie, so de Broglie, but it looks like de Broglie wavelength lambda equal to h by p, that is equal to h by mv. So we can say that lambda is inversely proportional to v. Now for electron, for orbiting electron, actually v is inversely proportional to n. Now see, lambda is inversely proportional to v, v is inversely proportional to n, so lambda is directly proportional to n. And now what? It's so simple. Lambda third excited state means lambda 4 upon lambda ground state. Lambda 1 is equal to n fourth by n1, and fourth is 4, n1 is 1, so it is 4:1. Oh, okay, they have asked about how it changed. So we can say that lambda 1, it will, we can easily write this, lambda 1 will be lambda 4 by 4. So wavelength will decrease by the factor of 1/4, or it will become 1/4 that of in third excited state, whatever be the your way to express the answer. Next, calculate shortest wavelength in the Balmer series of hydrogen? In which region? Infrared, visible, ultraviolet? So clear answer is visible, but will not give that answer uh, in the beginning. Okay, calculate shortest wavelength of Balmer series. So we know that for Balmer series the formula is lambda b, actually Balmer. So it is R, where R is Rydberg constant, equal to 1 upon 2 square minus 1 upon n2 square, where n2 is greater than 3, greater than 2 actually. So it is 3, 4, 5 and so on. So okay, for shortest wavelength, remember I told you that if lambda is short, means having less value, then frequency will be large, then energy will be large, then gap will be large. So if these are the energy levels, so largest gap will be obtained for infinite to 1 region, so infinite to 2 region actually, because it is Balmer. So for shortest wavelength, n2 is equal to infinite. So 1 upon lambda Balmer shortest is equal to R 1 by 2 square minus 1 by infinite square. So it is R by 4. So we will reciprocate it. So lambda Balmer shortest is equal to 4 by R. And if you could remember, I told you about the value of R, and in fact 1 by R. So that 1 by R value was 0.99 into 10 to the power minus 7. So it is roundabout 3.9 something, 3.9 into 10 to the power minus 7 meter. So it lies in the visible region. Actually it is close to that ultraviolet region, but yeah, it is just touching visible region, and it is violet, because shortest visible wave is violet. Okay, in Rutherford scattering or alpha scattering or Jiger-Marsden experiment, draw the trajectory traced by alpha particle in the Coulomb field of target nucleus. Explain how this led to estimate the size of nucleus. So in this question, what you can do, just draw, and there are some energy levels, actually electron orbits actually. So trajectory traced by alpha particle. So if it was going far from the nucleus, it has traveled without deviation. If it was little bit closer, then it was repelled. Actually I had to show repulsion from somewhere here. Anyway, you can show it from somewhere here, bending, from early bending, and very few repelled back. So the alpha particle, it is just for estimation of size of the nucleus. So in my video I have covered it in the section where I taught that distance of closest approach. So you can refer that, and here I am giving the summary. The alpha particles which okay, you can explain these also, that few alpha particle, many of the alpha particle went straight, and few of them were deflected from small angles, fewer at larger angle, and very few negligible amount of alpha particle bounced back. So now here the alpha particle which undergone head-on collision with nucleus could go to closest approach. So here, if this is the nucleus, charge of nucleus is Ze, and this is the alpha particle, so it bounced back, and this is the radius distance of closest approach. So at closest approach, kinetic energy of alpha particle get converted into potential energy of alpha nucleus system. So that's all, we did it. So kinetic energy of alpha particle is equal to k q alpha q nucleus upon r naught. So r naught is equal to k q alpha q nucleus upon kinetic energy of alpha, and that's all. Q alpha is 2e. We know charge on alpha particle is 2 unit, 2e, because there are 2 protons, and nucleus Ze, Z is number of proton in that nucleus, and upon kinetic energy of alpha particle. That's all. Oh no, we can conclude this, 2Ze square upon Ke alpha. That's all. But this is the distance of closest approach. But what about size of nucleus? So radius of nucleus is less than that r naught. So we can just estimate that, okay, nucleus is much smaller than that. So at least we can predict its radius. How would ionization energy change when electron in a hydrogen atom replaced by a particle of mass 200 times that of electron but having same charge? Well, इस क्वेश्चन का आंसर देने से पहले एक बार फिर से डेरिवेशन कर लेते हैं एनर्जी का. अभी प्रीवियसली एक काम करते हैं, पूरा शुरू से कर लेते हैं. तो हम कह रहे हैं कि सेंट्रीपिटल फोर्स इलेक्ट्रॉन, ऑर्बिटिंग इलेक्ट्रॉन लगने वाला इलेक्ट्रोस्टैटिक फोर्स के बराबर होता है. आई नो बहुत से बच्चों के लिए ये बहुत अनोइंग हो गया होगा क्योंकि रिपीटेडली एक ही चीज़ बार बार आ रही है, लेकिन गेस व्हाट स्टूडेंट, इसकी वजह से आप लोगों को बिल्कुल जैसे कहते हैं ना कि माइंड में प्रिंट हो जाएगा. तो पहले mv² एक r कट जाएगा, ये हो जाएगा k² अपॉन r. फिर उसके बाद क्रॉस मल्टीप्लाई कर दिया, एक r कैंसिल करके ये क्रॉस मल्टीप्लाई कर दिया, mv² r इक्वल टू ke². देन बोर्स क्वांटाइजेशन कंडीशन, ओहो ये भी ख़त्म हो गया, mvr इक्वल टू nh अपॉन 2 तो यहाँ से v निकल जाएगा, ये हो जाएगा 2 ke² अपॉन nh. इसे हम mvr वाली कंडीशन में रखेंगे, m 2 ke² अपॉन nh इक्वल टू ke² अपॉन nh अपॉन 2 क्रॉस मल्टीप्लाई कर लेंगे तो इससे आर, एम वी आर इक्वल टू एन एच अपॉन 2 पाई। तो आर की वैल्यू यहाँ से निकल जाएगी। मैं इस समय सब स्क्रिप्ट नहीं लगा रहा हूँ, यह केवल अपनी अंडरस्टैंडिंग के लिए है और आप लोगों के क्विक रिवीजन के लिए है। अपॉन 4 पाई स्क्वायर ई स्क्वायर एम के। अब काइनेटिक एनर्जी हाफ एम वी स्क्वायर, that is half k e square upon r. Potential energy माइनस के ई स्क्वायर, क्योंकि Q1 Q2 होता है, दोनों के दोनों, एक इलेक्ट्रॉन है एक प्रोटॉन है, तो एक पॉजिटिव एक नेगेटिव, तो दैट इज़ वाई नेगेटिव, और अपॉन आर। तो ये हो गया। अब टोटल एनर्जी दोनों को प्लस कर देंगे, हाफ एंड 1, तो आ जाएगा माइनस हाफ के ई स्क्वायर अपॉन आर। आर की वैल्यू रिप्लेस करेंगे तो ई इक्वल टू माइनस हाफ के ई स्क्वायर अपॉन आर की वैल्यू ये रही, एन स्क्वायर एच स्क्वायर अपॉन 4 पाई स्क्वायर ई स्क्वायर एम के। सो दैट इज वाई इट इज -1/2 4 पाई स्क्वायर ई टू द पावर 4 के स्क्वायर एम अपॉन एन स्क्वायर एच स्क्वायर। इसे कट कर देंगे तो इट इज़ -2 पाई स्क्वायर, ओ सॉरी, ई टू द पावर 4 एक्चुअली, ई टू द पावर 4 के स्क्वायर एम अपॉन एन स्क्वायर एच स्क्वायर। सो ultimately the thing is, in this question we can write that since energy of electron in nth energy level is En equal to -2 pi square e to the power 4 k square m upon n square h square. It means now the question is the mass of particle is 200 times that of electron, and they are not talking about its charge, so only variable is m. And according to this expression, En is equal to, I can put some constant capital C, and I am just interested in m and n. So if how would the ionization energy change? It means now ionization energy will be equal to E infinite minus O, one more thing, negative, so minus E1, that is at infinite it will be 0, and minus this Cm upon 1, that is plus Cm, some constant multiplied by mass. So mass has came here, so it will be the mass times that of if we talk about electron, then it will be mass times this thing. Now if particle for given particle mp, mass of that particle is 200 times mass of electron, that is m. So IE, ionization energy, will be equal to ionization energy for that particle in the place of electron is equal to C into mp, which is C into 200 m, that is it will become 200 times more, that is ionization energy for that particle will become 200 times that of ionization energy when electron is there. So So you can state the answer. It will become 200 times than the ionization energy when electron is there. 16th question, it is repeated one, so I'm not doing it. You can do, but I can do one thing. I can write Bohr series formula. And I can say for shortest wavelength, this N2 is equal to infinite. Why? I have cleared this thing earlier. And see, this time they have given the value of Rydberg constant, so you have to put this, nothing else. Oh, in fact, I think I should do this. So 1 upon lambda Bohr shortest equal to r is 10 to the power 7, 1 upon 2 square minus 1 upon infinity. And now I am reciprocating it. Bohr shortest is equal to 4, 2 pi square, 4 upon 10 to the power 7. Oh, nothing much change is here. Meter. This is what you should keep in your mind, that most of the time r is not given, most of the time it is given, and its value is they can give its value, accurate value is 1.097 into 10 to the power 7. They can give it like 1.1 into 10 to the power 7. They can give it like 10 to the power 7. So whatever it is, you have to put the value accordingly. Now the electron in a hydrogen atom is in its second excited state, means n equal to 3. Calculate wavelength of the lines of Lyman series that can be emitted through the permissible transition of electron. It's a very long question. So actually second excited state, this is first, second excited state means third. So for Lyman series, for Lyman series only 2 transitions are there, and we have to find the wavelength of both the transition. So for 3 to 1 transition, so for 3 to 1 transition, 1 upon lambda 3 to 1 equal to r, 1 upon 1 square minus 1 upon 3 square, that is equal to r. They have given it 1.1 into 10 to the power minus 7, and 1 minus 1 by 9. It will become 8 by 9. So 1 by lambda 3 to 1 is equal to, it is 8 by 9, and I am directly multiplying it with 1.1. So it is 8.8 by 9 into 10 to the power minus 7. Why I am not going to calculate this, I am reciprocating it. So lambda 3 to 1 is equal to 9 by 8.8. And see, this 10 to the power minus 7 will go into the denominator, and then we will take it in the numerator. So it will be plus 7. And 8.8. Now see my tricky calculation. It is little less than 9. So answer will be 1.1 into 10 to the power. Oh, sorry, I did some error here. Oh, big blunder. Actually r is in positive power, so now it will go up. Actually wavelength is in the order of this much. So that was human error. We all are human, yeah, but in exams these errors are not accepted. Okay, so that's all of it. Now second, for 2 to 1 transition, 1 upon lambda 2 to 1 is equal to r, 1 by 1 square minus 1 by 2 square, that is r 1 minus 1 by 4, that is 3 by 4. Oh, 3r by 4. Now reciprocate it. Lambda 2 to 1 equal to 4 by 3r. So 4 by 3 into 1.1 into 10 to the power 7, it will become 3.3, and if we divide 3.3 4 by 3.3, it will be approximately 1.2 approximately. So right now I'm not using any calculator, anything, any measuring device, but I'm just using those tricky method of calculation. So this is all of it. So you can calculate it, but I don't have enough time to do that. Now, a very nice question. An alpha particle moving with initial kinetic energy k toward a nucleus of atomic number z approaches distance d at which reverses direction. Actually, this is the concept of distance of closest approach. Obtain expression for distance of closest approach d in terms of kinetic energy. That's all. So first we will draw its diagram. This is ZE. This is our alpha particle coming, going. D this time it is. See, we can't use our symbols. Whatever given, we have to use that. So at closest approach, kinetic energy is equal to electrostatic potential energy at that instant. So kinetic energy is given as K, electrostatic potential energy 1 by 4 pi epsilon naught. Purposely I am writing it like this. Generally I use symbol K, but that will resemble with this. That is why I am not using that. So these are some tricky ways. You have to be aware about these. Otherwise, sometimes we do, even we, the teachers, do some error in that. So okay, here I'm writing its expression also. It is 1 by 4 pi epsilon naught q1 q2 upon r. So that is why it is like this. So once again we will do it like this. Q alpha is 2e, Q nucleus is Ze upon D. Now we will cross multiply this. So D equal to K will go in the denominator. It will be 2Ze square upon 4 pi epsilon naught K. It is looking like that relative permittivity or dielectric constant, but it is not that. I'm separating it, highlighting it. That's all. Find the ratio between wavelength of most energetic, means which has frequency highest. Most energetic means lowest wavelength. Lowest wavelength of Bohr and lowest wavelength of Paschen. So we have to find lambda Bohr lowest upon lambda Paschen lowest. We can explain this like most energetic means for most energetic nu is highest, so lambda is lowest. And for lowest transition for Bohr, 1 upon lambda Bohr lowest is R 1 upon 2 square minus 1 upon 3 square. Frequency is highest. Frequency is highest means frequency is highest means gap is highest, means it will come from infinite. Lambda lowest, lambda shortest, lambda means actually they are asking for most energetic, means high frequency means lowest wavelength, and lowest wavelength, that is shortest wavelength. For shortest wavelength n2, for all transition n2 is infinite. And in the same way for Paschen, lowest. So see how they are just changing the terms, changing the words and confusing the things. 3 square minus 1 by infinite square, we can directly use it here. You can start from here, and what I am doing, I am just reducing the work, so that is why I am doing it here and directly putting on that side. So okay, lambda, what else I can do? Just be careful what I am writing. Bal, who is this? Bal, who is this? Okay, Paschen lowest. So Paschen lowest, that is why I did this. So I can write what I did. I put it in the denominator. If you will solve this, you will get this. Alright, otherwise what you can do one step further, and from here you can find an expression for lambda BAL, and you can directly put here, but I'm going this way. So both way you have, try in that way, reciprocate this and then put the value, or if you understood this, then proceed accordingly. So now it is R 1 by 3 square upon R 1 by 2 square. Mean, extreme. R will get cancelled. So it is 2 square by 3 square, that is 4 by 4 is to 9. Write two limitation of Rutherford's model. First thing, unable to explain. Electron arrangement. Second, unable to explain complex spectra. And third one, stability of, actually two are asked, but I'm just writing third one also. Stability of atom, and then that total story, that orbiting electron, radiate energy, will radiate energy, then it should fall into the nucleus. But it does not happen. But so atom is not stable. So atom would not be stable. So this was the problem, and we know about this. Actually, Rutherford believed that to explain origin of his spectrum, he said that orbiting electron, it will radiate energy, and that is why we get that spectrum. But if it radiate energy, then ultimately it will fall into the nucleus. So he was unable to explain this. All right, next 12.5 electron volt electron beam is used. Okay, means that much energy electron beam is used to excite a gaseous hydrogen atom at room temperature. Determine the wavelength and corresponding series of the lines emitted. So here what we will do is directly, no further confusions should be there. Actually what will happen, E equal to E2 minus E1, but we are not worrying about this. What we are going to do is this. So E is equal to 12.5 electron volt, and first we will convert this into, okay, and here as we know we have to find wavelength. So E equal to hc by lambda, and that is equal to 12.5 electron volt. We have to change it into joules, so it will be 1.6 into 10 to the power minus 19. So lambda will be, it will come here, it will go there, hc by 12.5 into 1.6 into 10 to the power minus 19. Sometime, okay, sometime hc by E value is given. hc by E value is given. So in this question we could directly see this is hc by E. We could directly put that value here, but it wasn't given in this question, and I didn't I forgot to write it here, but in the exam sometime it happens, they give that entire value, and at that time most of the time student do these type of mistakes. No, I won't say mistake, but this kind of they just go through this method by which I am going, and make some difficult choices for them in these calculation. Okay, so 16 approximately 4s are, these are my approximate calculations, so need not to laugh at them. 4 3s are, 4 1s are, and this is, so it is almost 0.99. okay, because 3.1 is there and numerator is smaller, so it is like that, into 10 to the power minus 34 plus 8 plus 19, so it is 27 minus 7, 0.99 into 10 to the power minus 7 meter, and this corresponds to UV region. Next, the short wavelength limit of Lyman series of hydrogen spectrum is this. Calculate short wavelength limit for Bohr series. What is the meaning of that? Actually, short wavelength, once again I will say that they are talking about, we know that for Lyman, short is R 1 by 1 square minus 1 by infinite square. So, oh sorry, 1 upon lambda. So these are the mistakes. Oh, I had done the blunder. So that will be, it will come 1, and that will be 1 upon R, and 1 upon lambda Bohr short is R 1 upon 2 square minus 1 upon infinite square. So lambda Bohr short is 1 by 4, so 4 by R. Now we know that they have given that Lyman series wavelength is this one. We can divide both of them, but in a tricky way. Lambda, oh, kindly ignore those. So I think I have to just end this video here, because now more disturbance are there. So there are few more questions which I will cover in another video. So, but I will end this thing up. 1 by 4. So lambda Bohr shortest is equal to lambda Lyman shortest by 4. So it will be, I think some mistake is, oh sorry students, a big mistake is there, because Lyman upon Bohr, but I have written it Bohr upon Lyman. So I am correcting it. You people please correct this one upon that one. So it will be 4. Alright, so anyway, so sometime we teachers also did the mistake, but alright. So now 4 into 9, 1, 3, and I think I'm not even audible now. And if you multiply, do I have any tricky calculation here? Yeah, of course. 9 4s are 36, 13 4s are 52. Okay, oh, why I did this? So 4 4s are 16, 1, 4 3s are 12, 13, 4 1s are 4, 5, 4 9s are 36. One decimal place. Have I done something wrong? Ah, yeah, it's of course correct. That's all. So that's it for today, and there are 2-3 more questions. I will cover them up with the important questions of dual nature of matter and radiation. I hope you liked the video. Bye bye.